Good morning. Welcome to day 2 of the 230th meeting of the American Astronomical Society here in Austin, Texas. I'm Rick Fienberg, AAS press officer, and I'm assisted this morning by my deputy press officer, Larry Marshall, who is monitoring our online webcast, and by Benny Tsang from UT Austin, who is our Astrobytes media intern. He'll be handling the roving microphone during the Q&A. A couple of quick announcements for the press corps. We have a press dinner tomorrow evening and a press tour tomorrow afternoon, and there are sign-up sheets for those in the press office, so please sign up by the end of today because I need to have head counts by the end of the day. Finally, the online press kit is going to be updated this afternoon with links to the presentations from yesterday and eventually links from the presentations given today at the press conferences. For those of you who haven't been to a AAS press conference before, the way we do it is I will introduce the topic and all of our speakers. They will then give their presentations one after the other, and then we'll do the questions and answers at the end. And I'll ask you during the Q&A to please wait for a microphone so that the folks on the webcast will be able to hear the questions that you're asking. Okay, well today this morning the subject is inconstant stars. Stars don't always shine steadily. Many of those that do are kind of boring, so it's good that some of them don't. And today we're going to hear about a number of different kinds of inconstant stars, singles and doubles. And we have 4 presentations. The first one will be newly uncovered component of our Aquarii's northern jet. That'll be given by Rodolfo Montez from the Smithsonian Astrophysical Observatory. He'll be followed by surprises from an eclipsing Cepheid variable star from Thomas Kirkman of St. John's University. Then Lorne Nelson from Bishop's University will speak on the discovery of the shortest period pre-cataclysmic variable star. And finally, Chase Million from Million Concepts will speak on searching for flares from cool stars in GALEX data. So I will turn it over to Rudy, and we'll get started. I should mention that there are 2 press releases going out this morning for 2 of the 4 presentations. So if you're on the AAS press list, keep your eye out for those. All right.
Thank you. Okay, today the title of the press release that you can find is called Watching a Volatile Stellar Relationship. It's reflected here if you want the information sheet as well. I've summarized the results in this handy little 138-character note at the top there that you can all tweet out if you'd like to, including the hashtag for the AAS conference. This is work that I'm doing with collaborators at the Smithsonian. I have the list here: Margarita Karofska, Joy Nichols, and Vinay Kashyap. So our Aquarii is a symbiotic binary system. This means that it's 2 stars orbiting each other and they're transferring mass. In particular, it's composed of a red giant and a white dwarf, and that red giant is losing mass, and that mass is being dumped onto the white dwarf, and when it dumps it onto the white dwarf, energetic events happen. The stars are surrounded by this nebula that you see in this optical image from Adam Block from the University of Arizona. And you see all of this structure in that nebula. And I want to point out what you're seeing in an image so you understand how that relates to this energetic phenomenon. So that nebula, we think, was actually formed around 1070. And there's a historic record of this nova going off in the location of our Aquarii. And this material that you see is thought to come from that ejection. It's really composed of 2 biconical shells that are overlapping, and the material that you see in the ring is mostly coming from where that biconical shell is most dense. So most of the nebula that you see is actually coming from this intersection of these 2 bicones. The inner nebula is a bipolar planetary nebula, or I'm sorry, a bipolar nebula that was formed about 1770, so about, I can't do the math real fast, but around the time of the birth of this country, right? And so these optical images really tell you the history of the eruptions that are happening from this binary star, this symbiotic star. But what we're really interested in is studying the X-ray emission and what the X-rays can actually tell us. So Chandra, shortly after it launched in 1999, took a look at this object, and it studied it, and it found these two jets, X-ray emitting jets, so collimated flows of material coming off of this object. It was reobserved in 2003 and 2005, and those observations actually allowed us to study the motion of these jets. So when you look at this with X-rays, this is kind of what you see. Now this image has been enhanced a little bit. It's been smoothed a little bit to show some of the faint emission that I'm actually going to focus on. But the higher resolution images, which I'll show you some contours of in a moment, actually show you the structure in that jet. So all of this tealish color emission you see is actually X-ray emission, and it's jets that are actually aligned with that nebular outflow that you see in the object. So what you actually see when you look at the high resolution emission from this object is you see this inner jet, and so you see the point source in the middle. This is the first observation. You see the star itself is actually an X-ray source, and then you see these two jets that emanate from it, and one goes up and to the left and one goes down and to the right. This is actually an animation of, is it playing? Oh, yes, good. This is an animation of the three observations that we have, showing you that the jet is actually expanding. So you see the jet near the star is actually expanding outwards, and you see this new emission that appears in the far north, or the upper part of the image, near that little hook that you see in the optical emission, which is the grayscale image. That emission there is what we're actually reporting on today, because that emission wasn't seen before. It escaped detection because it's very faint emission, and only in our 2005 observation did we actually have enough signal to notice that it was there. And when we found it, we went back and found it in the previous epochs as well. Now, all of this emission, actually, because we see the motion of it and we know how far this object is, we can actually determine how fast it's traveling. And that inner jet that you see there, where you see most of the emission coming from, is traveling at about 630 kilometers per second, whereas this new jet material that we found that's way far in the north, near the hook, is actually traveling a bit faster at 850 kilometers per second. And that's surprising because we thought this jet structure was one continuous process, one whole ejection of a jet, and that jet was actually all seen throughout. But it now appears like these jets are from two different phenomena happening at two different times. And it gives us a better timeline of how the object is actually erupting, how the object is actually chaotic, and how it's volatile. So here I have a little toy timeline for you. On the top, you can see the old eruption that formed the outer nebula in about 1070. You have the inner nebula about 1770. And then we have this large jet that we're reporting on today. That large jet we can trace back to about 1950s. And that main jet that we see, we can trace back to about 1980s. And so we see this repeated appearance of these jets, and it really helps us understand more about the phenomenon of the symbiotic binaries and how they actually destroy, essentially, the star, start to throw material away from the star and lose that material into these nebula that you see all around it and through these X-ray jets. If you have any questions, or I'm sorry, I'll take the questions afterwards, but I'm going to repeat the tweet up here if you'd like to tweet it. I have my contact information there, and if you need these slides, I'm happy to share them with you afterwards. Thank you. I'll turn it over.
So I'm reporting work I did with 6 undergraduate students at the College of St. Benedict, St. John's University. Those students have all graduated, so I became kind of the designated presenter. I'm also going to report data from the American Association of Variable Star Observers. So the students, when it was clear, which is pretty rare in Minnesota, could walk a couple of blocks to our observatory and take data on the brightness of stars, and then in the end present a senior thesis on their results. The object that we were dealing with is this little red dot. You can see that it's associated with the Milky Way, but it's not actually in the plane of the galaxy. It's maybe best thought as being across from, the bright star Altair. But it's about 1,000 times further away than Altair is, and so it should be, other things being equal, about 1/1,000,000th as bright as Altair, which would have put it outside of the range of our pretty much amateur equipment. But in fact, it's made out of two giant stars. So one that is about 15 times the radius of the sun, another one that's about 25 times the radius of the sun. So this object was reported as a variable star a little bit more than a decade ago, and pretty much exactly 10 years ago, the American Association of Variable Star Observers launched a planet-wide observing campaign. So there's a lot of data out there on how this object has been behaving. So we think if we could see this thing as two objects, and of course we just see it as a single dot, we would see a large, pulsing, bright Cepheid star being occasionally eclipsed by a slightly cooler, smaller star. So we have major eclipses like what just occurred when we have the brighter star being eclipsed, and minor eclipses when the darker star is eclipsed. So all we can actually measure is the brightness of stars. So if we could observe a continuous record of the brightness, and we can't in Minnesota, right? We would maybe have in this 100-day period 10 or 20 individual observations. But if we could observe it, we'd see something like this, where you can see the individual pulses, and there's also this kind of, this sinusoidal variation, which has to do with the fact that the stars are elongated in the gravitational field of the other star. So just using 20 or 30 observations, we can use computer modeling to give us that pulsing period and to let us estimate that sinusoidal variation. So if we subtract that sinusoidal variation, the eclipses are now maybe a little bit more obvious. And if we break the pulses up into individual sections and then stack those, and then exclude data that where we think there is an eclipse, and then stack all of that data together, we should get something that looks kind of like this. But as a matter of fact, over this 10-year period we were taking data, things were getting worse and worse and worse. They weren't getting better. The dots weren't converging to the red curve. So for the last thesis, this is actually the results we were getting. So we were pretty much puzzled by how we were failing to converge to the proper behavior. And one of my students suggested maybe the thing is accelerating. So that would be pretty much a surprise. Usually we don't think about stars changing in a human lifetime, let alone in just a decade. And one of the problems with working with undergraduates is they graduate. So they might have suggestions of future work, but it in fact never gets done. So this year I was on sabbatical, so I had a chance to curate all of the data. So what we have is brightness through 4 different filters that we took ourselves, brightness through 4 filters that's available from the American Association of Variable Star Observers. So we have 8 data sets that we could take a look at. So I could fit all of that data, and we can see consistently, highly statistically significant, all of this data says we have the same sort of orbital period, a little bit more than 50 days. And again, consistently, highly statistically significant, we've got a pulse period. And then surprisingly, we have a pulse acceleration period that also is very much the same through all of this data set. So another way of presenting this data is to take a look at what that pulse period is as a function of time, and the red curve is our best fit model. So another negative surprise we had is we discovered in the literature that somebody had also measured that this object had a changing pulse period, but an increasing pulse period, not a decreasing one. So when we get down to look at that result, we see that in fact it wasn't a problem. In fact, where we had common data, they were actually agreeing. So the previously published result was actually using archive data before the object was at least announced to be a variable star. So the result is that sure seems that this object is not just increasing or decreasing its pulse period, it's actually sometimes increasing and sometimes decreasing. So the next question would be whether this is an erratic oscillation or whether it's actually periodic. Lorne?
Okay, good morning. I'd like to discuss a rather remarkable binary system that was discovered by our team that includes Saul Rappaport at MIT and Andrew Vanderberg at CFA. And if our interpretation is correct, then this is one of the, or is the shortest period pre-cataclysmic variable that has been discovered to date. After analyzing all of the targets in campaign 10 of the K2 mission, K2 being a reincarnation of the Kepler telescope that's designed to survey a diverse set of fields in the galaxy, it was discovered that EPIC 2012-83111 had a periodicity of 71.2 minutes based on 30-minute cadence observations. So the cadence is very close in magnitude to the periodicity, and this causes specific problems. So what you see in the light curve here is some rather deep eclipses that occur, and also a contribution that's sinusoidal outside of the eclipses. So in looking at this data, we can determine that the two stars are probably are eclipsing, and that they're probably quite small, and that one of them is very hot and is producing an irradiation that illuminates the companion star. So if we impose a toy model where we have, say, a white dwarf that is being eclipsed by an ordinary star, and say the eclipse lasts for 5 minutes, and we include an illumination effect at the plus or minus 10% level, then convolving that with the cadence of K2, namely 30 minutes, we get the blue curve that you see. So you can see that our model fits the data rather exquisitely. And so this is not, well, this was a very pleasant result as far as we were concerned. And we also knew that this particular target had been already identified in the Sloan Digital Sky Survey as WD1202, which is a 19th magnitude hot helium white dwarf. So, of course, it was identified as a single star, but we know that that it's actually a binary system. Now, in order to be certain of our results and to refine our model, we resorted to ground-based photometry that was of short cadence. We used several telescopes, and I show you on the left-hand side a light curve, the actual data taken at Observatory Mont with an 8-second cadence. And you can see that the ingress and egress of the eclipses are measured very precisely. So the blue line that you see there is actually our model fits. So the model fits the data quite nicely. And what you see here is an animation for that system to scale based on our model. You see the light curve in the lower left-hand side, and you see the eclipsing. Also, the system is seen almost edge-on, so the inclination angle is close to 90 degrees. One side of the companion star is highly irradiated, and the other side, of course, is quite dark. And during our observations, we never did detect the dark side of the companion. So the big questions are, how did nature form such a binary with a very short orbital period? And subsequently, what is the fate of this binary system? So to answer the first question, we have to invoke common envelope evolution. According to this scenario, you start with a progenitor binary that is composed of two stars. One star is more massive than the other star. That star evolves to become a red giant with a degenerate helium core. The giant then engulfs the companion star. The companion star subsequently spirals in towards the center, in other words, towards the core, concomitantly expelling the envelope of the giant. Now, this is a very difficult physical problem to simulate, but here is a simulation from Sebastian Ullmann at HITS, and you can see that the giant star is having its envelope basically expelled, and the orbital period is becoming very, very short during this process. And if you look at the chronometer on the upper right-hand corner of the simulation, you can see that the whole process takes place on the order of hundreds of days. So it's very, very fast. So based on our observations and our own theoretical models, we can conclude that the progenitor binary formed about 3 billion years ago. The mass of the white dwarf's progenitor was about 1¼ solar masses. The primordial orbital period of the original binary was about 150 days, so it was quite close. And this common envelope phase took place about 50 million years ago, so relatively recently on a cosmic timescale. We also determined that the companion is actually a failed star, namely a brown dwarf that has a mass of about 67 Jupiter masses. And we can conclude that that brown dwarf largely survived unscathed during the common envelope phase. So our conclusion is that this system is not a cataclysmic variable. It is the shortest period pre-cataclysmic variable that has been found to date. Only about 1% of white dwarfs have brown dwarf companions, so this is a rather rare system, but it provides us really with a unique test, the best test of common envelope evolution. We predict that this system will become a cataclysmic variable in about 250 million years as a result of the loss of gravitational radiation, or via gravitational radiation. And at that time, the brown dwarf will fill its Roche lobe, and it will be cannibalized by the white dwarf companion, and it will be a full-fledged cataclysmic variable at that time. So finally, I just note that this system is the poster child for the hot side, cold side model. We know that the irradiated hemisphere facing the white dwarf is extremely hot, the hottest temperature probably being very close to the temperature at the surface of the sun. And we did not detect the cold side. It's vital that that detection be made so that we can determine the temperature gradients and how the energy from the irradiated side flows to the dark side, so to speak. And I can tell you that there is a group who is currently addressing that problem. Thank you.
Oh, there's a big button. My name is Chase Millian of Millian Concepts. My colleagues are Scott Fleming, Rachel Austin, Clara Bersour, Bernie Shao of Space Telescope, and Luciana Bianchi of Johns Hopkins. We are searching for flares with GALEX. The foundation of this work is the observation that the sky changes rapidly. This is not obvious from looking at it. Obviously, a lot of people are researching the question now, but it's been relatively recently. It is obvious, however, when you look at the sun, because we know the sun flares a lot, and we've been looking at that for a long time. The question, the foundation of the work is whether we can go back in the archive and study very fast variables with archival data. The Galaxy Evolution Explorer spacecraft, or GALEX, was an ultraviolet all-sky survey that measured stars with integration times between 3 and 30 minutes. That's how the images were archived. But the spacecraft itself actually collected data with 5,000ths of a second precision. It recorded individual photon events with that precision. So a few years ago, I went back and started rebuilding the calibration pipeline to unlock that very short time domain data. We now have a database of 1 trillion photons. That's 1.2 terabytes big. I'm very proud of it. And we have a set of tools to generate new images and new light curves. This is an example here. There's a huge flare. This one was actually previously discovered in prior work by Welsh et al. During the mission. And there's also a satellite that streaks through the image. So the original images were 3 minutes to 30 minutes, and there's one of them. This is one 30-minute image broken up into 30-second frames. with G-photon. Here's the light curve for that flare. You can see it's very big. It goes from basically 10 counts per second to 2,000 counts per second. That's a lot of energy. If I were a living thing, I would not want to be in the way of this. While that's a very large flare, we know there are a lot of smaller flares, and based on just fitting a line, we predict that those smaller flares are going to be more frequent. At the same time, habitable planets are closer to cooler stars, and cooler stars we know have a lot of these flares. It may be that even though small flares are small, because the planets are closer, they will have more of an impact on the habitability of those planets. At the same time, the flares are very hot, so they're bright in the ultraviolet. The stars are very cool, so they're not bright in the ultraviolet. The contrast means that GALEX is almost uniquely equipped to detect these events. And with G-photon, we now have the time resolution, down to a second or so, to measure the energy of these flares. So what we've done is we've gone and we've compiled a catalog of M-dwarfs, about 10,000 known M-dwarfs with known distances. We've made G-photon light curves for all of them. You can see the previous plot went from 0 to 2,000. This plot goes from 0 to 2. So these are much tinier. The flares are about a minute long. Each one of these is from a different star. Most of these stars have a couple flares. We found about 100 or 200 flares of this size at energies that haven't really been measured before. So the upshot is now that we can measure the rates and energies of these smaller flares, we can start to draw conclusions perhaps about what impact they might have on habitability. I'm intentionally vague. This means something. I really do not know. It may be that flares strip away the atmospheres. It may be that they irradiate the surfaces. There's even a recent preprint where they said it may be necessary. Some amount of flare activity may be necessary for prebiotic chemistry. I don't know, but I'm really excited to get this result out so that other people can tell me what it means.
All right, thank you guys very much for very interesting results on stars that don't shine constantly. All right, we're going to begin the Q&A period here in the room. I remind you, please wait for Benny to bring you a microphone, and then please tell us who you are, who you work for or write for, and who you're addressing your question to. And if you're on the online webcast, please queue up your questions for Larry Marshall using the text chat feature. All right, questions from here in the room. Don't be shy. We'll start down here. Okay, I have one. Wait for the mic.
Steve Marin, freelance in Harvard University Press. I have one for Lorne and one for Chase. The cataclysmic variable that this will become, with just this little brown dwarf to supply the mass, do you have any idea of how big an eruption that can make? Is it going to be like a nova or barely a millionth of a nova?
Yeah, it's quite a low mass, and so the frequency of the nova explosions will be greatly reduced, and so.
But it can be a similar explosion.
Yes, that's right. Mm-hmm.
And then for Chase, if I'm not forgetting what other things GALEX did, I believe it saw one or more tidal disruption events.
Mm-hmm.
Does your new database improve the possibility of finding other TDEs that may have been missed?
It's entirely possible that we could find another one of those. I'm not counting on it, but yeah, we could. That'd be really exciting.
So you've created this database, but it hasn't fully been mined yet, right? So the community can now get access to it, is what you're.
Yeah, it's available to everyone, and these 10,000 M-dwarfs is our test. Mm-hmm. And then over the next few years, we're going to start mining it, and we'll make all of that available as quickly as possible.
Okay. Any other questions here in the room?
Could I just follow up on
please do.
Question? So for cataclysmic variables, there's generally a well-observed period minimum of about 80 minutes. And when this system actually comes into contact, so what we would call a zero-age CV, the period will be about 55 minutes. So it will be anomalous in that sense. We do certainly observe CVs with orbital periods of less than 80 minutes, not very many of them. No doubt some of them probably formed through the same type of mechanism that we're proposing for WD-1202, but others can evolve to very short periods if the donor was highly evolved and was losing mass continuously. And then basically you strip away all the outer layers, the envelope, and you're left with the sort of the core region, which is greatly hydrogen depleted and being primarily composed of helium. It's very small, so it can fit inside a smaller Roche lobe, and the period is necessarily shorter. So these highly evolved systems could conceivably evolve to a minimum period of about 5 minutes before their period starts to increase again.
Larry, do we have any questions online? Okay, I have a few questions. I'll start with one for Rudy. So you showed us an animation of the 3 different epochs of the X-ray data, and you showed that in the most recent one you had emission from that arc up at the very top. But it looked to me as I was watching the animation like there was something moving, that there was like a clump of X-ray emission moving in the 3 epochs outward, and that it aligned with that clump in the 3rd one. Are you sure you're seeing something that you just hadn't seen earlier because you didn't have the sensitivity, or is it that something in the jet has finally caught up to that arc? I mean, how do you separate those?
So you're talking about all in the north, right? All
in the far north, that little arc where you finally saw you had contours in the 3rd observation.
So we do actually see some emission in the earlier epochs, that emission that's moving upwards. Mm-hmm. That's how we're actually measuring the velocity.
Okay.
But that edge that lights up, we looked for it in the previous epochs, and we determined the sensitivity of whether or not we should have seen that edge, and we could have detected it in the earlier epochs, but we didn't. So it definitely lights up afterwards. But it is, I mean, your interpretation is right. These little clumps are moving straight up, mm-hmm. and then the edge of the emission is being lit up.
Okay.
And we actually can pinpoint when it lights up because we have an XMM observation that happened about 6 months before the Chandra observation where we see it. And spectroscopically, we don't see it there either. And so it's a very narrow window of when that edge lit up.
And just to give us a context, so what kind of speeds are we looking at as these jets are moving outward? Or are we looking at hundreds of kilometers per second, or thousands, or some other numbers?
So the inner jets are about 630 kilometers per second, and then this new jet that we found is 850 kilometers per second.
Okay. All right, and then I have a question for Tom. You described your observations as being consistent with the pulse period of the Cepheid changing. And I'm wondering if you have any thoughts on what might be causing that, and if you could tell us whether other Cepheids have been seen to have their pulse periods change.
So first of all, there's an easy and easily checked and almost certainly wrong possibility, but it would be by far the most interesting one, and that is if the Cepheid is in orbit around something else, so that we're seeing Doppler shifts of the pulse period. So it's not actually changing, it's just a Doppler shift effect. So that would require something like a 10,000 mass black hole, about 100 AU orbital radius. So it would be easy to check. We don't quite have the equipment to check it. It's probably more likely something like a relaxation oscillator would be my guess in the atmosphere of the Cepheid. Your second question was, do we see other Cepheids changing? And yeah, we do, but not commonly at this high rate. Mm-hmm. So this is a relatively fast change. So minutes per decade as opposed to fractions of minutes per century.
Okay. And I have a question for Lorne. I think you were showing us only primary eclipses, not secondary eclipses. Is that because the companion is so faint that you actually can't detect those secondary eclipses?
We had sort of a marginal detection of the secondary eclipse, but we'll need more telescope time in order to verify that.
Okay, and then when I think of a cataclysmic variable, I'm thinking of a white dwarf with a companion that ultimately evolves to a red giant and starts spilling material onto the white dwarf, but your companion is a brown dwarf.
Right.
So what is it? Is it the inspiraling of the orbit and simply the white dwarf heating the brown dwarf that causes the brown dwarf to ultimately expand and fill its Roche lobe and start spilling? I'm just having trouble getting my head around how the brown dwarf is going to dump material onto the white dwarf.
Okay. Yeah, what's going to happen is the orbit will shrink. So the separation will shrink due to energy and angular momentum losses due to gravitational radiation. So gravitational waves will basically carry away the energy and angular momentum that will force the two objects, their separation, to be continuously diminished until, because the white dwarf obviously is not going to fill its Roche lobe being so small, until the brown dwarf actually fills its Roche lobe, then it will start to overflow the Roche lobe, and the whole mass transfer evolution will be basically driven by gravitational radiation losses.
And then the other thing is that the brown dwarf itself has so little mass that, you know, it doesn't have all that much to contribute to the white dwarf.
No.
So do you expect it to be, this may be similar to what Steve asked, you know, should we expect one small explosion or a series of small explosions, or, you know?
Well, right. So the frequency will be greatly diminished as well. And so nova explosions might take place every 100,000 or a million years, something like that. But the main reason for that is that the mass transfer rate is very, very small for these low mass donors. And so consequently, not much mass gets transferred. So it takes a long time to build up critical mass on the surface of the white dwarf before a thermonuclear runaway can occur.
Okay.
In other words, a classical nova.
Okay.
Can I follow up?
Sure, right from the mic. Thanks.
So you have any number in your head for how much mass you need to be that critical mass, so that we know how many critical masses there are in the total mass of the brown dwarf? Are we going to get one nova explosion or hundreds of them?
Well, it's an exponential decay process, but things are changing continuously. So we could expect this to happen, to occur for many Hubble times, I would suppose. Well, and perhaps until the brown dwarf actually becomes planet-sized, in which case then the equation of state changes, and there are a number of physical changes that have to be taken into account. But while it's a brown dwarf, I would say that it requires about 10 to the minus 5 solar masses to be accreted before an explosion will occur. And if this happens every million years, it means that the mass transfer rate is about 10 to the minus 11 solar masses per year. So you could look at it conversely and say, given that our models show that the mass transfer rate is about 10 to the minus 11 solar masses per year, and that the critical mass is about 10 to the minus 5, it's going to take about 1 million years for each explosion.
Okay.
So I think that gives you the physical context to see that this is a very long timescale type process.
So the AAVSO really needs to do some recruiting here. Any questions online? No? Okay, I have one more question for Chase. Did you deliberately seek out the GALEX data on previously known M dwarfs, or did you just look for flares and then ultimately trace them mostly to M dwarfs?
Right now, we are looking specifically at M dwarfs that are known to have been observed by GALEX.
Okay.
We are going to expand our search to stars with less certain designations. Mm-hmm. So we will have a catalog of flares that do not necessarily correlate to known stellar parameters, and hopefully that information will get filled in over time.
Mm-hmm. Okay.
But I expect that catalog of flares with unknown stellar parameters to have like 200,000 events in it.
And would you expect to find flares from solar type stars that are analogous to the flares that our sun emits?
Yes.
Okay, so that's all in there too. Okay, very good. Okay, good. We got two questions, one here and then one here.
Yeah, this is for Chase. So you say you're...
Can you please identify
Oh,
yourself?
sorry. My name is Jason. I'm from, actually, University of Hawaii. So my question for you is, when you're mining through your GALEX data, do you get any kind of... Are there any sorts of false positives do you get? And if so, how do you filter them out? How do you know that they're false positives?
Yeah, that's pretty much the primary issue and what my presentation tomorrow is going to be on. We're working on different algorithms. Clara Brasseur in particular is helping a lot with that. We have a low false negative rate based upon just manually searching through the data, and about 50% of our detected flares are false positives. Once we get to like millions and millions of stars, that might be unworkable. So really, our work for the next 6 months probably is going to try to do that. And the way we verify is I actually just go through every one manually and say that looks real, that doesn't look real.
Okay.
Dr. Hansen, German Public Radio, that's for Tom. Will you follow up on your object, or and are there any ideas how long such an relaxation phase lasts?
So, I mean, it looks like it's a decade scale from the previous results. I have a lot of gray hair, so I'm not sure I've got another decade in me, but I certainly am going to be following up for the next few years. And of course, the American Association of Variable Star Observers has a really long history of following up on stuff.
Okay, any further questions? Well, if not, we'll wrap it up. I want to thank the speakers again and thank all of you for your attendance. We have one more press conference this afternoon on galaxies, clusters, and voids. That'll be here at 2:15 Central Time. And then tomorrow morning, we'll have another press conference to wrap things up. So thank you all very much, and we'll look forward to seeing you here this afternoon. Thank you all.
Thank you.